Alright, so moving on, a body of revolution and principal axis of the body at point A. So if your rigid body of interest is a body of revolution, then it is easy to identify not only one principal axis, but you can identify all three principal axes, at least three principal axes which are perpendicular to each other at a point which is on the axis of the body of revolution. What do I mean by all that? I will explain. First, let me explain what is meant by a body of revolution. What is meant by a body of revolution? Now, first of all, this word revolution has nothing to do with the angular velocity of a body. Nothing to do with that. With omega mf. So do not let this confusion even begin in your mind. This word body of revolution has nothing to do with angular velocity. This word revolution has to do with how possibly a rigid body can be generated plane or using an area, how you can generate the volume of a rigid body. So on the right hand side I have volume of a rigid body, how it can be generated by a planar area. How a volume can be generated using a planar area by this process of revolving. So the word revolving has to do with the process by which a planar area is converted, can be converted geometrically into a volume. Okay, that's the scope of the word revolution. So let's focus on this scope only. Suppose I have a semicircular area as shown here. Okay, so this is a semicircular area, and let's consider an axis like this. And then you sweep the area, you sweep the area about this axis. Sweep, or rather I should just use the word revolve the area. Revolve the area about this axis. Which axis? The dashed line. 360 degrees. That sweeping will, this revolution will lead to this creation of a volume. In the geometric sense, of course, physically if you take an area and you just revolve it, it will remain an area. I am not talking about that physical sense of revolution. I am talking about the process of revolution keeps creating more matter. So the area will keep creating more matter as it revolves around this axis, and it can result into the creation of this volume. Since an area is being revolved about an axis and it gives rise to a volume, this is called, I will call this as a body of revolution. In this way, we want to use the word revolution. So if a semicircular area is creating a body of revolution using this axis, what I have shown here, this will become a sphere, right? And this sphere is a body of revolution. Where is the axis about which the revolution has taken place? That axis is also here. right? This is the same axis. We can call this as axis of evolution. Similarly, if you take a right angled triangle as the planar area, and you try to generate a body of revolution using this axis, what will you get? You will get a cone. The axis of revolution be somewhere here. This is, if this is h, this will become the height of the cone, and if this is b, this will become the radius of the circular base of the cone. Okay, gives a cone. What happens if I take a rectangular area, and try to create a body of revolution about this dashed axis? What will that give me? That will give me a circular cylinder I am drawing here. Again, if this is height, this will become the height of the cone, height of the circular cylinder, and if this is the edge length of the rectangle, it will result into radius. That will become the radius of the circular cylinder. So these are examples of body of revolution. Another example, if you take this circular area and you revolve it about this axis, which is not passing through the area. In all the previous examples I showed, the axis was coinciding with one of the edges of the planar area in each case. Here I have a situation in which the circular area is here and I intend to revolve it 360 degree about an axis which is not passing through the area. What will this generate? What volume we will have here? That volume, this body of revolution will be a torus. My figure may not be very accurate, but it will be something like this. Like a donut, right? A donut will be created. Something like this, with this cross section being circular cross section, and this axis will pass somewhere like this. Okay, so this is also a body of revolution. Now, many rigid bodies that we come across are bodies of revolution, and if your body of interest is a body of revolution, then I am going to tell you how we can identify principal axis of the inertia of the body passing through a point. Let's focus on this body of revolution, which is a circular cylinder. Circular cylinder, clearly this is a body of revolution. Now if you take a point A, okay, anywhere, I don't intend to put A at the center of mass. I am putting A here, okay, and I want to know the P axis My question is, can we find by visual inspection? Can we find by visual inspection a set of three mutually perpendicular MP P-axis of IA tensor? That's my question. Can we find a set of three mutually perpendicular axes? Yes, by visual inspection we can find all those. How do we find that? By using the idea of plane of symmetry. Recall, if I can identify a plane of symmetry that is passing through A, in this case, let's consider this plane of symmetry. I consider this plane of symmetry. So this plane of symmetry is dividing the cylinder into two parts, front part and the back part. I hope you can visualize, not that difficult. Plane of symmetry, front part and rear part. Right, there is this plane of symmetry. What does it mean? It means that if you now consider an axis which is perpendicular to this plane of symmetry, which is almost like coming out of the screen, because I try to draw this plane of symmetry as the plane of the screen itself, plane of the screen. It means that the axis that will come out, and let me call it XE1 axis, must be a P axis. X1E1, which is perpendicular to the yellow plane of symmetry, must be a P axis. Right? But then this is not the only plane of symmetry that this rigid body has. The fact that this body is a body of revolution, there are infinite planes of symmetry, infinite vertical planes of symmetry. If I take a plane like this, if I take a plane like this, which is also a vertical plane, so this is also, I am trying to draw this as a vertical plane passing through A, and mind you, A in this case is, it is already given, I did not mention it explicitly, but A is a point on the axis of revolution. It is given. The cylinder is a body of revolution and A is a point on the axis of revolution. Again, keep in mind, I am not talking about nothing about omega mf. nothing to do with omega, nothing to do with omega mf. When I call a line as the axis of revolution, I mean the axis with which the body has been created from a planar area. Omega mf of this body can be in any direction. Omega mf is out of context. Alright? A is a point on the axis which has been used to create the body of revolution using a planar area. Okay, yellow plane was one plane. I am now drawing an orange plane which is also passing through A, but I have chosen the orange plane. Orange plane is perpendicular to the yellow plane. I can always choose that. This plane is also a plane of symmetry. This orange plane is just second of the infinite number of planes of symmetry that pass through A and are vertical, oriented vertically, as we are seeing the diagram. What does this mean? If orange plane is also a plane of symmetry, if the orange plane is also a plane of symmetry, it means if I orient x to E2 perpendicular to the orange plane, that also must be a p-axis. Same argument. And since the yellow plane is perpendicular to orange plane, x1 E1 is perpendicular to the yellow plane itself, and x2 E2 is perpendicular to the orange plane, it means the x2 E2 will also be perpendicular to x1 E1. Right? So I drew x1 E1 in this way. I'm going to try drawing x2 E2 on the same figure. I know these are figure is getting cluttered, but if you watch my video, look at the notes, I am very sure you will be able to figure out what I am trying to say. Because this cluttering doesn't happen all at once, gradually I keep putting more information while I speak. Thus I believe if you watch my video, you will still be able to understand what I am trying to draw here. So x2 E2 is another axis which will be perpendicular to x1 E1. And x2 E2 is also a p-axis. Now if I go ahead and draw the third axis, x3 E3, which is perpendicular to both of them, and that x3 E3 axis is going to be parallel, or rather I should say x3 E3 axis is identical to the axis of revolution. You can always choose that. Okay, so I'll write here, now choose x3 E3 as the axis of revolution, same as axis of revolution. Now you have a set of three, or before that, if x3 E3 I choose as body along the axis of revolution, mind you, x3 E3 is also a p-axis. I have said this earlier, last class I said, if x1 E1 is p-axis, x2 E2 is p-axis, then the third axis which is perpendicular to both x1 and x2 is got to be a p-axis. You get that information for free, right? That's what is happening. By symmetry argument, I say x1 E1 is a p-axis. By symmetry argument, I say x2 E2 is a p-axis. And since x3 e3 is an axis which is perpendicular to both x1 e1 and x2 e2, it means x3 e3 is also a p-axis, right? If x3 e3 is also a p-axis, then we have found a set of three mutually perpendicular p-axis for a body of revolution. Okay, so for a body of revolution with a point A being on the axis of revolution, you okay, form a set of three perpendicular axes which are p-axis of the RB at point A. If you go ahead and choose this, if you go ahead and choose two more axes, x1 prime e1 prime and then x2 prime e2 prime, which are mutually perpendicular and their plane perpendicular to x3 e3, even these three axes is a set of three mutually perpendicular p-axis. You have many choices. With x3 e3 as one common axis, you can choose an infinite set of three mutually perpendicular p-axis if the body is one of revolution, as I showed, and the I inertia tensor that you are interested in is of the body at point A, and A is the point on axis. Okay. Since you are able to identify these axes, in this case you must choose. You must choose we choose A x1 e1, x2 e2 and x3 e3 as our working coordinate system. Okay, and it will give us the desired outcome that your I matrix will have at best only three non-zero components. Rest of them will all be zero. I have shown this simplification for a cylinder but the same arguments will follow for any body of revolution. You consider a body of revolution like this, like a lampshade, and then you have axis like this, and then the point about which you want to find the angular momentum is on the axis. Okay, in this case again you choose any axis as x1 e1 which is perpendicular to this, call this as x3 e3, choose this perpendicular, choose another axis perpendicular to this, it will give same thing. Inertia matrix is a diagonal matrix. Alright. Several problems that we will deal with in this course will indeed be bodies of revolution, and then go ahead and use the simplification by choosing the coordinate system to be as I have shown, using the principal axis of the RB at A. Alright. Now the next thing that we are going to do is to find the full inertia matrix of some bodies of common shape. And I am assuming that these bodies have uniform density. Okay. And also I am going to find the inertia matrix of such bodies of common shape at their center of mass. Okay. You will realize that so far in this course I have whatever I have talked about the inertia matrix, I have not really done any integration per se to find exactly what the various components of the inertia matrix would be. I'm going to do that now, and I'm going to do that integration process for very simple shapes like that of a cuboid as I have shown. We will also do that for a thin disk, and we will do the same thing for a circular cylinder. Trying to find the inertia matrices of these three shapes will be again good enough for the problems that we will see in this course. However, the process, as I explained, is crucial to be understood properly, and the hope is that if you understand the process clearly, even if you come across some complicated shapes, you will be able to find the inertia components by integration. Alright, so let's find. So I have been given a cuboid. C is the center of mass, and my working coordinate system is this. We are being asked to find the inertia matrix of the RB at its center of mass. Now in general, IC will have 6 independent quantities, 6 independent integrations to be performed. But for this body, we can identify some planes of symmetry passing through point C. And if I can identify some planes of symmetry passing through C, I can conclude that some of the off-diagonal components will be 0. In this case, we have x1e1, x3e3 is a plane of symmetry. Passing through C. Okay, which implies that x2e2 is a p-axis. Right, which means IA12 will be 0 and IA13 will be 0. Sorry, IA12 and IA23 will be 0. Right, IA12 and IA13 will be 0. So IA12 will appear here, this is 0, and IA23 will be 0. It means this member is 0. Since inertia matrix is always symmetric, this 0 means that this is also 0, and this 0 means that this is also 0. So out of 9, 4 are 0. But then I realized that x1 e1 and x2 e2 is also a plane of symmetry. Of RB at C, which implies that x3 e3 is a principal axis, or alternatively I can say that IA13 is 0 and IA23 is also 0. Right, x1 e1, x2 e2 is a plane of symmetry, which means x3 e3 is a p-axis, and since 3 is a p-axis, IA13 will be 0, IA23 will be 0. So IA130 means this is 0, and IA230 we have already, it's the same repeated conclusion, there is nothing new. But the moment I said this to be 0, I also know that this element will also be 0. So the inertia matrix for the cuboid at its center of mass will only have off-diagonal components. Will have only off-diagonal components. So let me call that as IA11, IA22 and IA33. These I need to find. Now let's assume that the edges of this cuboid are known. So this is A, this edge is A, known, this edge is B, this is A, and this edge is C. Let's use these symbols to denote these known values A, B and C. Now I need to find IA11, IA22, IA33 in terms of what? In terms of M, total mass possibly, A, B, C. Now I am using C, the letter C, for two things here. I would like to clarify. Capital C is the center of mass, and small c, little c, denotes the one of the edges of the cuboid, that edge which is parallel to x3e3, as I have marked on the figure. Okay, so this is little c. I need to get these three components in terms of A, B and C. That will require integration. We will do the required integration. So IA11, let's start with IA11. That by definition is this. You go back to the previous lecture slides, this is what we had as the definition of IA11. What is dm? Dm would be a small chunk of mass, maybe here, right? Dm, and it is in the neighborhood of a typical point P, which has coordinates as x1, x2 and x3. Referring to which coordinate system? Referring to this coordinate system. Okay, so the x2 and x3 that are appearing here are nothing but the second and third coordinates of the location P, around which I am considering a small chunk of mass dm. Okay. Now this integration is actually a volume integration. It's over the whole body. Over the whole body. Right? Let's try to do this integration process. I have IA11 as body, x2 plus x3 dm. Now I'm going to write this dm as rho times dx1, dx2, dx3. What are these new things? So the small chunk of mass that I showed on the previous slide in the neighborhood of this point P, dx1 and dx2 and dx3 are the dimensions of this small cuboid. It is a cuboid within a cuboid. This is an infinitesimal cuboid. Okay, and this infinitesimal cuboid had dx1 is the length of edge, which is parallel to E1, and similarly dx2 is the length of the edge, which is parallel to E2, and dx3 parallel to E3. Okay, recall E1, E2, E3 are oriented like this. E1 is like this, E2 is like this, and E3 I drew like this on the previous slide. You see, this is E1, this is E2, and this is E3. So this small chunk of mass, small cuboid, has its three edges correspondingly parallel to E1, E2 and E3. Okay, so in that way dm is this, where rho is density of RB material, right? So density times volume, dx1, dx2, dx3, the product is nothing but the volume of the infinitesimal cuboid. The moment dx1, dx2 and dx3 appear, I would like to now write this integration in a more precise manner as triple integral. This is a triple integral now. x2 dx3. It's a triple integral where the three integrals are over the three independent variables. The first one, I will say it goes from x1 equals minus a to x1 equals plus a. Minus a by 2 to by a by 2, right? Because the length of the edge length which is parallel to E1 is a long, right? The length is a. C is the center of mass, and that is also the origin of our coordinate system. So when you are doing the integration along E1 direction, what is the limit of that integration? Or when you are doing the, in other words, when you are doing the integration with respect to x1 alone, the limit of that integration should go from x1 equals minus a by 2 to x1 equals plus a by 2, right? From here to here. That is why I am writing these limits. X1 going from minus a by 2 to plus a by 2. The second integration will be describing the limits on x2, and that will go from minus b by 2 to, maybe I write it on this side, more clearly. X1 goes from minus a by 2 to plus a by 2. X2 goes from minus b by 2 to plus b by 2. And finally x3 goes from minus c by 2, small c by 2, to x3 plus c by 2. Okay. Can we handle this integration? Can we do it? Yeah, it is quite straightforward. It may be a little bit lengthy, but it is possible to do this. I am skipping the steps here. I expect you to do it on your own. I think with the kind of exposure you have to performing such integration, you should be able to do this. Now, mind you, rho, I am assuming rho to be a constant, which means that rho can as well be pulled out of this integration. This is what you will have. When you perform this integral, I'll give you the final answer. Try to get that. It will turn out to be this is what it will turn out to be. Rho times ABC, b square plus c square by 12. But then we realize that ABC is nothing but the volume of the cuboid. Volume of cuboid. Okay. And rho times ABC must be the total mass of the body. Total mass of body. So this can be written as simply this. This is IA11. So IA11 does not depend, it depends on mass, depends on B and C, but A does not appear explicitly. So there are three edges, or rather three edge lengths are there, A, B and C. A was the length which was along the even direction or the one direction. So when you are trying to find IA11, that length does not appear explicitly. A does not appear here. It's about B square plus C square by 12. It turns out to be like this. Complete this. This is a homework. Once you have IA11, you can actually recognize the pattern that is appearing in IA11 expression and write the expressions for IA22 and IA33 directly without again repeating the integration process for those. And those patterns are very easy to recognize. See, IA11 is turning out to be B square plus C square by 12, right? And the cuboid was, let me draw this for quick reference here. This is the cuboid. Okay, so I was calling this edge as A, this as B, and this as C, and C, this is x1 E1, and this was x2 E2, and this is x3 E3. So A goes with E1, B is parallel to E2, and C is parallel to E3. So IA11 is this. You recognize the pattern. You can write IA22 without doing any integration. It will again have M, it will have 12. Instead of B, it will become C square, and instead of C, it will become A square. This is what IA22 is. IA33 will be M by 12. C will become A square, and A will become B square. Okay. Pattern recognition. Or alternatively integrate and get this answers. Do the full integration if you want, but for me it is enough to do one integration and write the other two by doing this pattern recognition. So coming back to the full expression of IC for a cuboid, this is the inertia matrix, okay, relative to this coordinate system that I have drawn. A standard result. Once we have done the integration, you can keep this result in as a reference result. You can go back and use this directly. No need to perform this integration over and over again. BC, CA, AB. So this is for a general cuboid. Now suppose you have a thin plate. We use this kind of phrase, thin plate. So thin plate is also a cuboid, but it has one of its sides, one of its edges very small, very small compared to the other two edges. So let's take that thin edge to be C in our case. So I am saying we know that C is much less than A and C is much less than B. Okay, so it becomes a flat plate, something like, which I can easily draw like. So you are dealing with a situation like this. Thin plate. This is the center of mass. This is A, this is B, this is x1 E1, this is x2 E2, and x3 E3 is perpendicular to the plane of the plate, and along that edge I have this C, which I am saying is extremely small compared to A and B. What will be its inertia matrix about its own center of mass? One way is to, of course, go and do all the integration, right? And the other way to get this is simply refer back to this set of result and impose the condition. What condition? This condition and this condition. What do you get? You will get this. This is what you will get. Right? C is much less than A, so effectively this just becomes A square. C is much less than B, so this effectively becomes MB square by 12. And then there is really no simplification possible here, so this becomes that of a plate. So another useful result. Indeed, we will solve some problems where there is a plate, there is dynamics of plate involved, and we would like to come back and use this matrix, inertia matrix components. All right, I stop here.